there you are now. Welcome back to the workshop. Today we're going to have a look at stripping an engine. This is the engine from the red roof purple race car that you might have seen in the HRE Uncut video. If you haven't seen that, it'll be linked up here in the corner now. Go have a look at that and you'll get an idea of what the story is with this car. So I'm going to do a strip down of this engine and I'm going to have a look at all the major components to make sure that there's no undue wear or there was no problems when the engine was assembled by the last person. So this is my first time seeing this engine. I didn't build it before, so I always like, before I put an engine back out into service, that I know it from top to bottom so that I can have some confidence in the way it's built. So we've a couple of areas to look at. We're going to strip down all the ancillaries first, then we're going to take out the camshaft and inspect it. We're going to take out the crankshaft and inspect it, and inspect the likes of the timing chain and the bits and pieces for wear. The cylinder head has already been taken off this engine. It's over and has been pretty much repaired. It needs a new set of valve springs and some valve stem oil seals, which we're just waiting on them to arrive into stock, and then we can put them on. The gearbox is for another video. It needs to be stripped down and it needs some machining work done on it, so we might make another video of that in the future when we get around to doing that particular job. So I hope you enjoyed the little video and we'll get into it. So all of the basic ancillaries have to be taken off in order to check all the treads, to check the depths. Even just straight away in doing this, I found a couple of problems already. One being that the holes here in the top of the cylinder head haven't been countersunk. The top of the engine block haven't been countersunk properly, so that these studs are actually bottoming out. So we'll countersink them properly, and that will mean when we go to put the motor back together, the stud can reach full tread engagement rather than sitting on top of the block. It's not a good idea to have studs sitting proud of the top of the block, in other words not going all the way in, because it can cause a stress riser on the top of the block, which can lift your head gasket or cause poor sealing of your head gasket. People often ask me why I don't use air tools to take engines apart like these. There's a couple of reasons. One of the reasons I don't like using air tools is quite simply because you've no feel. And when I'm taking an engine apart, I'm trying to understand what has happened, how the engine has gone together, where potential problems might occur. When I use hand tools like sockets and spanners, I can feel the tread. I can feel how the stud wants to go in and out of the hole. I can feel how the bolt wants to go in and out of the hole, and it gives me an idea of where I need to look next. If you just strip the thing with no care given, then it's hard to actually tell when you have a problem or when you don't have a problem. It's sometimes personal preference. It's just the way I tend to like to do it, and I can get an idea for what's happening. This one's been put in there with a bit of Loctite, I think. Okay, so this is a really good example of what I was saying to you about taking an engine apart and getting to know it. So this pulley, I've just taken the center bolt out of the pulley, and the pulley should literally just slide off the end of the crankshaft. It shouldn't be on there at all tight, but this pulley is absolutely welded onto the end of the nose of the crankshaft. Now, there'll be one of two reasons for that. Either one, they didn't prepare the nose of the crankshaft correctly when they put the pulley on in the first place, or two, they used loads and loads of Loctite putting in the bolt and it seeped down between the pulley and the crankshaft. This is not good for a couple of reasons. One, this pulley should be able to float on the crankshaft because it is what sets preload on the sprocket for the camshaft, which I'm going to show you in a few minutes. If the pulley is tight on the nose of the crankshaft, then you don't know if you're getting the proper preload, and then you can have a problem where the double gear, well I imagine in this it's going to be a double row chain, a duplex chain, is pinched or isn't pinched in this case, which could result in basically that sprocket being able to move on the nose of the crank, which would affect your cam timing. It would eventually damage the keyway in the sprocket and would allow this to turn and could potentially fail. Remember, we're talking about a race item here. This is an engine designed for a race car, so everything has to be just so. And the fact that this pulley is on here so tight is a really good example of something that is not just so. We're going to have to go and get the pullers now to actually get this off. Okay, so I have my puller set up here, so I'm pulling on the actual pulley. I have a bolt in the end of the crankshaft, and I'm just using my hydraulic Sykes Pickerman pullers here. And it is working beautifully well to get this pulley up off the nose of the crankshaft. Like I said, you shouldn't need to use it. It shouldn't be a thing. Once you let that bolt off, this pulley should just slide straight off. You could tap this off with a drift or a hammer if you didn't have a pullers like this, but this is just a sort of a better way of making sure that you're going to get the pulley off in one go without causing yourself any great damage or causing the pulley any damage. These hydraulic pullers are absolutely the business, but they do have one weakness. They don't have a huge range of motion. So while you get great power out of them, they can only move the pulley a short distance without need to be reset. So that is a little bit of a pain, but it's reasonably straightforward. So there's the pulley off the nose of the crank. So it wasn't Loctite that was holding it. Okay, so we found the source of why this pulley was tight here on this bit of a close-up. You can see these grooves in the end of the crankshaft just at the tip of my, or in this pulley should I say, just at the tip of my marker. We'll have a look at the nose of the crankshaft and see if we can find the source of these grooves, and that'll be the reason why the pulley was so tight. Okay, so here's another few witness marks of another bit of incorrect assembly of this engine. You can see where the timing chain and the timing gear here have been rubbing on the housing and have been eating into the housing. Very shortly that was going to become a hole in the housing and a really bad oil leak. This will already have damaged the seal. So let's have a look and see what was causing that. Okay, this is a really good reason why we stripped this engine down. You can see here how this keyway is completely cocked over at an angle. So what's happened here is that the pulley has not been pulling down on the cam gear, or well, the chain drive gear. It hasn't been pulling down on that chain drive gear properly, which means that the gear has been able to move on the nose or on the end of the crankshaft, which then means the only thing that is keeping it in time is that keyway. The keyway is strong, but the crankshaft has softness in it there. So if it is constantly hammering back and forth, back and forth, back and forth, eventually it starts to bend that keyway over, which is what we can see here. And then if it keeps going, if we hadn't caught this when we did, what would have happened was the key would have eventually failed and the chain sprocket would have just spun on the nose of the crank, which would put the whole engine out of time and would have caused the engine to, probably best case scenario, lose a valve. Worst case scenario, could have really badly damaged the piston, damaged the bore, or damaged the cylinder head. So this is a really good find to get to right now, and a real good reason why, if there's other suspect problem with an engine, it's really worthwhile just stripping it all the way down and then back up again, because then you know what you're starting from. The likelihood is, if an engine has been put together in other areas wrong, then the likelihood is they have missed things all along as well. Another thing I want to show you here is, this is the throw out seal. So what this does is it's a throw out oil seal protector, and it is even marked with front on it. See the letter F? That's marked with front, telling you that this is supposed to be fitted to this crankshaft in this orientation. It was fitted in that orientation, which, as you can see, there's a raised bump here, which raised it up and caused it to sit up against the seal, which is why we've seen those witness marks on the inside of the timing chain cover. Another telltale here is I see all kinds of hammer marks here on this, what is a lovely set of timing gears. You see these hammer marks along here. This is a sign that somebody has been in here with a big heavy steel punch or something like that to turn up this lock tab, which wasn't needed. Okay, let's strip this a little bit further and see what the camshaft is like. Yet another example of the wrong washer being used to hold down the timing chain tensioner. You can see it's split. Okay, so in this clip you can see I'm using the pullers again that I used earlier on. It may not be completely apparent, but I am putting a lot of force on this pullers. I'm using pretty much all that pullers has to give to get that pulley off, which is just saying how much or how badly damaged the nose of this crankshaft is to hold this gear on here with so much force. Okay, so as we go deeper we find more and more problems. Look at this. This shim is all broke up. Not only the top one, but all the shims underneath are all broke. All broke into pieces, like. Each one of those shims should all be the one piece. And they're coming off in bits and bobs. What happened here, again, the same thing. The force was not on the shim the way it should be. The shim moved around, fractured and failed. Okay, so I've taken the camshaft out now and we're going to inspect it. So we're looking at the cam lobes and we're looking at the profile of the cam lobe. Now this cam lobe is starting to give problems. You can see by this sort of real rough grated surface on top. This should be completely smooth. It should look like here. It should have this really smooth surface to it, machined, ground, polished. But you can see it's the opposite here. It has this kind of grated surface. But that is nowhere near as bad as comparison to this one here. So what you can see in this one, and I'm just going to turn the profile for you to see it at another angle. So if you look straight down along the cam, you can see that this top is completely flattened over here. So what has happened is as the cam is coming around, it has picked up metal off the follower, and that metal off the follower is working like an abrasive to literally grind the top of the lobe of the cam straight off. The evidence of this is in these cam followers. So I just plucked out a couple of cam followers to show you here, and you can clearly see all the pitting in the top of the cam follower here. See all these sort of little dinks and divots. I'll just move it around for you to see, get a good angle on it. So it has all this sort of pitting and crustation on the top of it, which is bits of metal from the cam follower coming off and becoming part of the cam itself. I'll show you what a good follower looks like. So there's what a good follower looks like. It has an even wear pattern all the way around on the surface and is completely flat. That's what you'd want to see out of your cam follower, as opposed to these ones where you can see the clear divots, lumps missing out of the cam follower, which have picked up and damaged the cam. So why has this happened? The reason why the cam has failed in this manner is quite simple. I've seen this 100 times before. The valve springs that were fitted to this engine were way too heavy for this cam profile. That's one reason. The second reason is that more than likely the proper break-in procedure wasn't used. And from what I can see here, these cam followers look like they're incredibly heavily worn. Now, I don't know this for a fact, but I'd be inclined to believe that what has happened here is old cam followers were reused. That's what I think has happened here. By the look of the way these cam followers are worn, the wear on this cam follower is not typical of one that had run for such a short period of time in an engine. This is wear that I would see typically on a cam follower that has done a lot of hours. So I think three things have come together to cause this failure. One, incorrect running in of the cam originally when the engine was started first. Secondly, valve springs that were way too heavy. I measured the valve spring pressure on this over the nose for the lift profile of this camshaft in excess of 300 pounds. Mental amounts of spring pressure, no need for that whatsoever. That'd be for an engine that was going to spin to the moon 10,000 RPM or something crazy like that. This is an A series mini. If it sees 8,000 for even a short burst, it'll be a lot. Okay, next thing to take a look at is the crankshaft to see what's happening there. Okay, so I have you zoomed in here on one of the bearing journals. This is bearing journal number 3, and I want you to see the big difference in color here. You can see a bright shininess here and a kind of a bluing going on over here. So what's happened is we've had bearing failure here on the big end journal number 4. I just want to show you something here. I just poked my screwdriver in here and I'm picking out grey paste. That grey paste is white metal after coming off the bearing as it failed. So again, this we'll have to measure this crankshaft pin. It may have survived, but if it hasn't, it'll need a light polish or a regrind. But we have saved a major failure. The next thing that would have happened here is this conrod would have came apart, and you would have had the engine would have dropped a conrod and probably completely destroyed itself. Okay, let's go over to the bench and have a look at the pistons and conrods. Okay, so this is piston number 1 out of the engine, and I'm going to show you on this one how I check them, and then I'll do the same on the other 4. Well, the other 3. So the first thing you want to check for is a visual inspection. So you're looking at the piston to see if there's any gouges out of it, any lumps missing, and we're checking the top edge of the piston here to make sure that it's sharp and clean. So there is a tiny little bit of sign of overheating here, but it isn't anything major. It's well within capacity of being cleaned up and reused. The next thing we want to check for is wear on the ring lands. So we're checking for clearance between the top of the ring land itself and the top of the ring. So how we test that is by pushing a feeler blade in between the ring and the ring land. I can't even get my smallest one in here, 0.05 or 0.05. I can't even get that in there, which means these ring lands are spot on. They're absolutely where they need to be. To use my phrase, they are tight as tuppence. So what that tells me is that we've no great wear on the ring lands. As I said, I'm happy that the piston itself shows no great wear. The next thing we do is we put the piston in the middle of the conrod, or the conrod in the middle of the piston, and we check both sides to see where the gudgeon pin lands. This gudgeon pin is landing with the conrod in the middle, fairly close to dead on center. So I'm happy with that. The next thing then we're going to check is just visually having a look at the conrod to see if we can see any signs of cracking, fractures, overheating or wear, and they look really in good nick from that point of view. The last thing then is the bearings, and we see that problem that we've seen in the crankshaft. So here you can see complete bearing failure. Okay, so the white metal has been stripped off this completely and it has been taken down to the copper. In order to ascertain why this bearing has failed like this, I'm going to have to do a little bit of investigation. I need to get the crankshaft out now, and I need to put some measures on it to see if it's the crankshaft that's at the problem. If it isn't the crankshaft that's the problem, then only one of 2 other things that would cause bearing failure like this. There might be distortion in the eye of this conrod. So we'll have to bolt that conrod together and measure it with a dial bore gauge to see if there's distortion in the eye of the conrod. If there's no distortion in the eye of the conrod, then it was oil starvation or oil failure, or the wrong bearing being used. It could be any one of those 3. So we'll go get the crankshaft out of the engine now and have a look at that and see can we find why that bearing has failed. Okay, so we have the crankshaft out on the bench and we're going to take some measurements. Let's check these big ends first, given that that's where we've seen the big problem. So we have 44.20 millimeters on that one, which is exactly 10 thousandths over size. So that kind of adds up with the bearing I'm checking. Check this one. So that's just coming in at 44.18. Little bit of wear, but would still be okay. Check this one and see where it comes in. So 44.19. That's okay, that's within tolerance. This one here, we'll call that 44.20, same again. 44.20. Okay, so that tells us that these bearings are within spec. They're within plus or minus 0.01 of a millimeter of the factory spec. So the factory specs for plus 10,000 oversized grind on the big ends is 40.20. So that's telling me that the problem isn't in the pins of the crankshaft, which I didn't really think it was in the first place anyway. So the next thing I'm going to check is the bores of the affected conrods. Okay, so here's one of the good conrods, and I've just torqued up the conrod bolts so they're right. I've set this dial bore gauge so that when it reads 0, it's going to be the correct dimension for this bore. Okay, So let's put the dial bore gauge in there, and I'll just sweep either side of it, and you'll see that it's just coming up to the 0 mark there, and that is exactly where it should be. So sweep up to it again. So that one is exactly on spec. Let's check one of the ones that failed. So dial bore gauge in here again, and check to see what measurement we get, and we're seeing undersize. Okay, so we're seeing undersize in that plane. See, it's coming up, it's not making the 0. Okay, try and give you a better angle at that. So you see we're not coming up to the 0. Let's turn this conrod now through 90 degrees and see what we get there. So we're going past the 0 there. Okay, in either plane we're going past the 0. So what that tells us really clearly is that these conrods, the end hole of these is not round, so that they're out of round. So they're flat in this direction and they're wide in this direction. And that makes perfect sense, because when I tried the bearing in, the bearing is flopping around in one direction and it's sitting high in the other direction. So what the problem here is that these conrods are out of round, they're oval. So they have a teardrop shape rather than a round shape. So the way of repairing these is we're going to have to skim the tops of these caps, we're going to have to bore the conrod, and then we'll have to hone it to bring it back to correct size. So what has happened is this engine was assembled with conrods that were out of round, they weren't measured, and the result of that is bearing failure, and we've seen big end bearing failure as a result. Okay. I hope, guys, you enjoyed following me in the workshop for this little particular look at how I tear down an engine, and hopefully it's give you guys a bit of encouragement that you might, if you're working on engines yourself that are an unknown quantity, at how much value there is in stripping down a motor to get a feel for exactly what it is. At the worst case, it's a bunch of gaskets. You can put the motor straight back together again if it has no problems. But look at it this way, if you strip it down now, find the problems like I did, you're preventing failure in the long run and massive expense. A couple of gaskets and a bit of time now saves so much expense. If I have just put this engine back together for the customer, replaced the damaged camshaft, fixed the gearbox and put it back for the customer, it would have lasted maybe only another few laps of the race circuit, half a test day, and it would have failed again. And this time it would have failed catastrophically. So by spending an extra little bit of time in the workshop pulling the motor completely down, we've caught a load of problems before they become really exponentially expensive to repair. In this case, a couple of bearings, polish the crankshaft, bring those conrods back into true, and this motor can go back together again, and we'll have caught all those problems. All right, I hope you enjoyed the video, lads, and don't forget, if you're new to the channel, to hit subscribe. If you enjoyed this video and you'd like more content like that, give us a like, a thumbs up. And don't forget, we love comments, so give us comments in the comment section below, and if you have any questions on anything that you've seen here and you want me to answer them, same again, bang them in the comment section down below and I'll try and do my best to answer it. After that, see you in the next one.